Okay, welcome back to the next installment of AVR timers. What we're going to look at today is we're going to look on the screen here and we're going to see that we can actually create a pulse like this on a fixed schedule, and we can change the width of the pulse. And why we're going to do that is we're going to use these two output compare values. We're going to continue to use output compare register 1A as the point in time in which the counter overflows back to 0. But we're going to also use output compare register 1B at a point in time when we get another interrupt. And during that interrupt period, we're going to turn on the LED. So at this time, we're going to turn on the LED, and here we're going to turn off the LED. Now notice that B comes before A in this sequence. That's the way it has to work in these timers. Overflow can happen at R1A, but not R1B, okay? So here we go, here's our interrupt routines. Again, we're using our compare A vector and our compare V vector. So what we've got here is the LED turning on when it gets to time for point B and turning off at time for point A when it overflows. A couple of other little changes here. I've just changed this so that there's a prescaler of 1024, and I've put the two values I'm going to use into the output compare register, and then of course I've activated two interrupt masks. Okay, I have to interrupt. Both of those have to be set so that we get both interrupts, okay? And of course, we're back using interrupts, so that means we need our header file for the interrupts. So let's just have a little look at this. What we've got is 19531, so that's this point in time here. And we've got 18531, this point in time here. So what we're going to do is we're going to have a look at how we might actually calculate those. I think, you know, if you put your thoughts into it, you would probably find that you can do this now yourself. So what I'm going to do is I'm going to switch over to the camera, stop the share of the screen, and I'm going to tilt the camera down and have a look at the diagrams I've created here. And this is actually the code running on the breadboard at the moment. Okay, so I've just taken that code and pretty much compiled it and put it into this. So let's have a look at this. Now, of course, this is upside down. I just need to find my video settings for Zoom and rotate that. There we go. Right, so what we've got is we've got our counter, and I'll turn some lights on. This makes it a bit clearer. So what we've got is our counter values. This is 18531, and this is 19531. Okay. Now, just as a ballpark, think about it. Our full counter period from 0 to 65535 is 4 seconds when we've got a prescale of 1024, as we do in this situation. So we should be looking at, you know, less than 2 seconds. You know, we've got 65535, we've got about 20,000 out of 65,000, so much less than 2 seconds, okay, is our value for this point in time. Just to give you a rough ballpark of what's going on. But of course, we know our model now. We know that it's the prescaler, the period equals the prescaler over the frequency times the compare value plus 1. Okay, so I'm just going to do that like that. And we can now start working out what these two values are. So I can work out what this overall period of time is because I can put in there 19531 as my compare value. So that's 19532 because I'm adding 1. And the prescaler, of course, is 1024, and the frequency is 16 meg. And that gives me a time period of 1.25 seconds. Okay, so that's the whole period of the whole thing here, 1.25 seconds. Okay, now we've also got this point in time here, 18531. So plus 1 is 18532. And again, 1024 is a prescaler, 16 meg, and what that gives us is a value of 1.186 seconds. Okay, so that's 1.186 seconds. But at this point in time, we haven't actually answered the question because we want to know how long it is on for. Okay, So that's what we really need to do. And of course, it's 1.25 seconds minus 1.186 seconds is of course 64 milliseconds. So that's how long our pulse is. And I'll just bring this over here and you can have a look at it. And that pulse is 64 milliseconds and it happens at 1.25 second increments. Cool. So let's just hop into share screen mode again, and we will have a look at what it looks like in the simulator. So I've got the simulator here in Atmel Studio. So what I've got is I've put the code in here. The only difference I've made here is for this board is the fact that the LEDs are on different pins as to what they are in the notes. So I've just changed it to pin B1. So that's B1 there and B1 here. I've changed that. So what we're going to do is we're going to start this, and we'll probably stop it around about here on its initial steps. So I'm going to start that, and I'm going to get it all ready, and it should be all fired up after the next step in the code here. And so you can see that already I've used 45 cycles of the microcontroller, 2.81 microseconds. So I'm just going to zero that at that point to make our readings a bit more accurate. And we're going to wait now for this 1.186 second duration until the LED comes on. Now, of course, that's going to take a while. The simulator is not running at the same rate as real life at all. It cannot do that, but it is busy in the background, ticking away and working out for us a time at which it's going to hit this interrupt. So we can just pause it at any time and see that we're up to, oh, there we go, we're up to 776 milliseconds. So what's that? We're a bit over halfway through it. So we'll just keep going. We're heading for 1.186 milliseconds, 1.186 seconds. There we go. So there we go, we've hit it now, and you can see that the period has 1.186047 microseconds. So that's 1.186 seconds. There we go. So we're pretty close to that. Now the LED should turn on for a period of time of about 64 milliseconds before we get to the next count, which is output compare register value A. So that's this point up here in our code. So if I just push this, it shouldn't take too long because it's only 64 milliseconds. So there we go. There's our cycle count there. I didn't zero it for that, but I'm going to actually tick this off now and let that go around until it turns the LED back on again. And you can see from this, looking at the counter stopwatch here, that our total period is 1.25 seconds, pretty close, within 47 microseconds of that. So that's pretty accurate, 1.25 seconds. Of course, in real life, you'd measure this with an oscilloscope. But what we're going to do now is we're just going to wait for the LED to turn back on and then just check that we're getting a pulse, an on pulse of 64 microseconds. So we should be coming up to that a little bit soon. Okay, I can keep waffling on, but there we go. It's hit it now. I'm going to set my cycle counter back to 0 so that I can check to see how long it is for this pulse. And here we go. There we go, 64 microseconds. So that's how long our pulse is. So I've just gone through and checked that. Now let's go back to our exercises and see that as we go down here, the first exercise, let's thinking about this in terms of electric fence. So we might want a pulse that kicks a huge coil in an electric fence controller, and it needs to apply power to that coil for a certain amount of time so it can build up enough magnetic field around it so that when it collapses, it gives you a very good spark, okay? So these things generate quite a bit of voltage. As part of that, of course, we need a ground return, so these electric fence units have a ground wire on them. So from the previous exercises, we've got 1.25 seconds as the full period. That shouldn't be in there. Just edit that out. Okay, and the on time was 64 milliseconds. So that's how you work that out. Now let's go down here. So we want to change this. Our electric fence has a pulse of 35 milliseconds every 0.75 seconds. So we're going to have to use a slightly different model for this, but really it's just a matter of reconfiguring the existing model. So I'm going to flip back over to stop share, and we're going to go back to the camera. There we go, you should be back on the camera, and we'll have a look at a slightly different version of this. So we're going to change our numbers. We're going to, let's go, we're going to go up here. There we go. We're going to have this output compare register 1A is, and the time period here we're looking for is 0.75 seconds. Okay, and then we want a pulse width, output compare register 1B. So this period in time here is supposed to be 35 milliseconds. Okay, so we've got a duration, a full duration here of 0.75 seconds. So of course, what we need to do is we need to work out this time so we can work out the value of B. Right, so that of course is 0.75 seconds, 0.715 seconds. Right, so let's just have a look at this. 0.715 seconds. So we need a model for this. Our model for is just really converting this one around the other way. So that's pretty easy. Our compare value equals the period we want times the frequency over the pre-scale, and that's -1. So that's really quite straightforward. The period we want is 0.715 seconds times 16 megahertz over a prescale of 1024 -1, and that gives us a compare value of around about 1117. It's probably 1. It's not an exact value, so I need to either truncate it or round it up, so I can have a play with those values, but that will be the compare value. And of course, this is the B compare value. The A compare value, this value here, what we're looking for here is 0.75 seconds times 16 megs over 1024 -1. So what we get there is we get up with a value of 11717. Okay, so that's how we would do this. Hopefully this gives you an idea of how you might generate a short kick pulse or something. So that, and all I've got it doing is just generating a simple blink on an LED. Okay, and we can play with that around. Just remember this one thing: if you see a number that pops out of here which is greater than 65,535, then you need to double check your math. Just always keep that in mind that what you're dealing with is 16 bits. And of course you can't use any decimal points here. They're meaningless because they're just bits inside a 16-bit register, which is like an int value. Okay, it has no decimal points. Okay, so there we go. We'll leave that with the other one. There's one more exercise on that page, which is to calculate a 35 millisecond pulse, but the actual duration is 2.7 seconds. So, some of those numbers will change a little bit actually. Cool. Now, I hope that has been a useful and scintillating exercise, and we'll just finish up there. Cheers.